welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody watching us, binge watching us from the future, preparing for the exam. So today is the last lecture in which we will have new material. I will simply go through this and finish. Next week we'll have a wrap-up of the course. We'll have a big quiz game where everybody can participate, a little bit like Eisgage 100. And you will play against all the TAs who will be here. I hope a few of them. And then that will be it. Then we'll let you prepare for the exam. The date was announced. It's in January. I think 21st, 23rd, one of the two. I have two courses. August 21 or 3. I don't know. Okay, so let's go through the material. Before that, I will ask you a few questions. It will also help me wake up because it's 8 a.m. So here is my question to you. Which of the following adjectives qualify a well-designed query language? 4 proposals, 2 of them are correct. Functional, imperative, low-level, declarative. And by the way, it's August 21st. I just checked. August 21st at 2 p.m. And normally you should receive the information in your mailbox. Okay. So nobody says low level. That's great. Means that data independence is well understood. Imperative is losing grounds. Functional is gaining grounds. Declarative, many people agree. And the top 2 answers are in fact correct. Indeed, functional and declarative. Declarative means that you just say what you want. Like think of SQL, select from where and so on. You say you want the projection and the selection ordered by this and that. This is declarative. Functional means that you can build the queries in a Lego game fashion. You can nest a query inside a query, which you cannot really do in Java or C++, but when you have a language like SQL or as we will see JSONic, then you can actually nest the queries inside the queries, just like you nest the tables inside the tables. There is some duality here. Low level, no, because the whole point of data independence and the whole point of designing query languages and database management systems is so that people do not have to do anything on a low level. It's supposed to be all hidden. So basically, the engineers who design the system go through all of that trouble and agony of implementing in the low level in such a way that nobody else will ever have to deal with that again. So this is the whole point of data independence. And imperative, that would be a language like C++, Java, and so on. And then you tell the computer what to do. But again, the spirit of data independence is that you don't have to tell the computer what to do. You just write your query and that's it. And then the work of writing it in an imperative language is done by the engineers who implement the system, not by the users of the system. For whom does that make sense? Okay, so declarative and functional. But why? Is it so that queries can be parallelized, that we want a query language to be functional and declarative? Or is it so that an optimizer can make the query faster than it would have been with the literal execution of the user's query? Or is it in order to delegate the details of the execution of the query to a machine rather than doing it yourself? Or is it because queries are more concise and easier to read and understand? Multiple answers possible. Why should a query language be functional and declarative. Think of data independence. Multiple answers possible, so you can put in every answer that you believe is correct. So see what you're saying. You like answers B, C, and D. Answer A is not very popular. Okay. Well, in fact, everything is correct. All of that are benefits of a functional and declarative query language. And the parallelism, we haven't, well, we talked about it with MapReduce and Spark, but in fact, I will show you how we can actually also parallelize SQL, JSONic, anything. So all of these are good reasons, right? Sounds great, right? To have all of these benefits from well-designed query languages. Okay, so now I'm going to switch back to the slides. Then we'll take it from there. You just need to let the computer do whatever it needs to do. Exactly, now it's there, okay? So I wanted to ask you these two questions to remind you of the context of why we are doing all of that. Why did we rehearse SQL? Why did we see SQL again with Spark SQL? And now why do we have yet another query language that is also functional and declarative? And as we will see, SQL is for tables and JSONic is for collections of trees. Okay. So this is where we are. You see, we're almost done. User interfaces, we leave out of the scope of the lecture, but I'll say a few words next week. So just to remind you of why we did another language and why SQL is not good enough, because a lot of companies are trying to push SQL as also being the solution for collections of trees. But here's the problem. When you have simple queries, that's fine. You add a few dots to SQL, you add explode and lateral view and so on. But as soon as you have more complicated queries, and it doesn't need to be complicated in English, like what are the top committers for every GitHub event, something that simple, and this is how you end up implementing it in SQL using all the syntax. And this is how it simplifies if you have a language that was designed for semi-structured data, for collections of trees. Okay? So now we are going to dive into JSONic. You've already had many tutorials during the semester in order to make it a bit smoother so that not everything will be new to you. Who followed the tutorials this semester? That's great. All right, so it will make it easier for you to understand what I will explain today. Okay, the first thing you notice, by the way, but I'll come back to that, is that order by, group by, you see, you recognize the for is a little bit like the from, the return is a little bit like the select, but you see it's actually very similar, but with a lot more expressive power. Okay, so this is the data set I told you about last time, the GitHub data sets that we also use at the exam. So you will also have a small part of that on the exam computer. It's nested and heterogeneous. You have 100 attributes in every event, but in total, there's 1,300 different ones. So you have a lot of sparsity and a lot of missing attributes or extra attributes. And you have mixed types. It means that the same path can be an integer in some events, in some objects, and it can be a string or an array in some other objects, right? Event, by the way, has nothing to do with databases. Event is a GitHub term, right? In GitHub, they call it an event. So each object corresponds to a GitHub event. When somebody pushes to a repository, when somebody commits, and so on. All right. And again, the overarching goal is to have data independence with JSONic, just like we have it in SQL. We can have it on top of Spark, on top of MapReduce, on top of HBase, on top of anything, right? On top of also reading the data on your laptop. All right, the language doesn't change. An illustration of this is where I stopped last time, is that this is a query that asks for all the keys that there are in a data set. If you use SQL, it can be inconvenient, right? Because if you just download a data set on the internet that you know nothing about, you don't even know the schema, you have no ideas what there is in there, there is something called data discovery, where you try to explore to understand what the data set is all about. So you don't even need to know the schema, you don't even know the columns, and you have 1 trillion objects in there. With just these lines, you can actually get all the keys, all the columns basically of your objects, right? So here we iterate over all the JSON objects. JSON file just reads from a backend. It can be anything. Here it's S3, where you put the S3, you can package it as a URL. Then you have the name of the bucket and then the name of the object, which may include slashes because that emulates a file system, but that will cover, right? It's just a bucket ID and an object ID, really. So when we iterate over all of these objects and we feed it into the keys function, right? There's a function called keys. That function is outputting as strings a list of the unique keys. In that case, maybe just 2, foo and bar. But the thing is, it works exactly the same if it's a small data set that is sitting on your laptop, or if it's a petabyte scale data set on an Amazon cluster. It's exactly the same query, right? And it will spit the two keys in that case. Okay. It works for JSON, it works for Parquet. You know, it's exactly the same query for JSON or Parquet. But now think a little bit. Now the physical implementation of that, right? On the logical level, it's the same. You have a collection of trees, JSON or Parquet, you want to know the keys. Who thinks, so what do you think is going to be faster? It's the same query. Do you think it's going to be faster with the JSON dataset or with the Parquet dataset? Who thinks it's going to be faster with the JSON dataset? Who think it's going to be faster with the Parquet dataset? A lot of raised hands. Why? Why is it going to be much faster, like massively faster with Parquet? Can anybody tell me? Or on Zoom?
Yes,
yes?
on Zoom is a binary format.
So this is part of the explanation. So, but the binary format means that it takes less space. But there is something even more than that. You don't even need, who understands that if you have a Parquet format, you do not even need to read the data? Why do you not even need to scan through the data with Parquet? There is a schema, yes. In a Parquet file, you first have a schema, and then you have the data. But what do we want here? We want the keys. Who understand that they are in the schema? Right? All you need to do is look at the schema. So you don't even need to look at the data. You can have petabytes of data. Just open each file, look at the beginning of the file with the schema, and take the keys, and that's it. So you see the magic of data independence is that it's exactly the same query, but magically turns out that this implementation is going to be much more efficient and faster than this one. But for the user, it's the same. Right? Okay, who is with me on that? Okay. So again, remember, it's exactly the same query. It's just magically faster depending on the implementation. Now, there's a huge ecosystem of languages. It hasn't consolidated like SQL. SQL is completely undisputed. I don't even think anybody in the world would dare suggest another language than SQL to query tables, flat tables. But we cannot say the same about trees. Somehow, it hasn't consolidated yet. It was clear already 20 years ago, even to the inventors of SQL, that we needed a different language for trees. SQL was not good enough. So some of the ideas behind these languages were also contributed by the inventors of SQL themselves. But the problem is that first, it took a while for people to understand this. And even today, a lot of people still try to force SQL to hit it with a hammer and hope that it's going to work on trees. But the problem is that what happened, there was a turning point at some point that suddenly people started understanding that we need a language, but then they started inventing plenty of them. Like every time somebody discovers and has the epiphany within a language, it just invent a new one. So now we have like 30 plus languages that are out there that kind of do the same thing. They are at various stages of development. Some are fully standardized, others are just a draft or a tutorial, but this is the ecosystem. What I'm going to do today is I'm going to teach you JSONic for various reasons. First, it's one of the oldest ones. It's already 13 years old. It's actually highly overlapping with xQuery. It's borrowing from xQuery, which is a standard. There was plenty of companies like IBM, Microsoft, Oracle, and so on that contributed to xQuery. And JSONic is basically the same as xQuery, but for JSON instead of XML. So that's the reason, right? There's been several, like more than a decade of efforts by a lot of very smart people from database companies, right? So I will go through that for this reason, but I don't know what will happen in 10 years if the market consolidates or anything, but what I can tell you is that the features will look more or less the same, right? The big ideas behind the language, it's just a matter of learning a new one, but just like learning Python, you can easily learn Java or many other languages, okay? So we'll focus on the concepts. Everybody ready? Okay. So when you design a query language, let's put ourselves in the head of a query language designer to do it cleanly without rushing. When you design a query language, you first need to decide what the data looks like, the data model. We call that first-class citizens. The first-class citizens of a query language is basically the objects that it manipulates, right? In SQL, that would be tables. So the data model in SQL would be tables that have rows and columns. Some of the columns can be primary keys, right? And you have sets or lists or bags of records, and that gives you a table. That would be for SQL. We need to do the same for JSONic, right? And we would do the same for a query language for graphs, for a query language for cubes, and so on, right? So we need to say what we are manipulating on the data independence level, right? Declarative and functional. So first, it's called JSONic, manipulates JSON. So we're going to have strings, we're going to have numbers, booleans, and nulls. In fact, we're going to have many other types, right? But all of that we can manipulate. But we don't manipulate them one by one, as you would do with Python or Java or an imperative language. Typically, we have a language that manipulates millions, billions, or trillions of these at the same time. It means that the first-class citizen of the data model here is a sequence of items. And sequence of items, I will probably repeat 100 times until 10 a.m., so don't worry about that. It's just because everything is a sequence of items. What does an expression in JSONic consume? A sequence of items. What does an expression in JSONic produce? A sequence of items. Everything is a sequence of items, right? So a sequence of items is just a flat list ordered of items. It can be heterogeneous because we're talking about collections of trees, right? We might not have a schema. So that sequence of items can be a huge mess. You might have a mixture of some integers and some strings and some objects and some arrays and so on, all mixed with no order at all, right? No order in the sense of no pattern, right? Completely mixed. So it's fully generic. Now you see how already SQL stops at that point. SQL cannot do that. SQL can only process homogeneous tables, right? That all have the same attributes. But in JSONic, we can have heterogeneous sequences of items. It means that if the data is not clean, that's still fine. You can still open it with JSONic. The second thing is that the sequences of items can be denormalized in the sense that the items do not need to be atomic, flat. The items can be trees. It means you can have objects and arrays as items. And remember, when you have objects and arrays, these are complex structures as opposed to atomic structures. So string, integer, boolean, these are all atomics. But if you have an object and an array, it can nest. You can have an object in an array, in an array, in an object, in an array, in an object, in an object, in an array, and so on, just like the Inception movie. Okay, so this is what you end up with a tree. And that we've seen in the data modeling lecture, that when you have JSON, objects in arrays and so on, you end up with a tree from a data modeling perspective. Who remembers that? Right? So we have trees. Okay. Then the next thing to know about sequences of items is that a sequence of one item is the same thing as one item. It's a canonical identification if you're a mathematician. We just consider that there is no difference between a single item and a sequence of one item. Okay? Sequences are flat. You cannot nest them. If you have a sequence and you try to put it inside another sequence, it's always flattened, just like the flat map in Spark, if you will, right? So here you combine a sequence of two items with a third item that gives you a flat sequence of three items. You never nest sequences. There is never a sequence in a sequence. If you want to nest, you need to use arrays. Arrays can nest. Sequences, it's only the outer level and they cannot nest. Okay, but the reason we do that is that we can have them by the trillions, the items in a sequence, because it's all flat. Okay, a sequence can be empty. That's totally fine. So a sequence can have 0 items, 1 item, 2 items, 3 items, a billion item, a trillion item, a quadrillion items, right? And finally, the items, but that I've already kind of implied, every item can be an atomic item, string, integer, and so on, can be an object, can be an array, or, and that I'm not touching that today, but just so you know, it can also be some function. In fact, that could be a machine learning model or an LLM or whatever, could be a function that you can also have in an item, right? But to not overcomplicate things, you can forget about that. For today, we will not have any function items, right? Atomics, objects, and arrays. Who is with me? So everything an expression in JSONic takes and produces is a sequence of items. That can be billions of items, can be fully heterogeneous, can have nestedness with arrays and objects and so on. Okay, everything is a sequence of items. Now, what's nice about sequences of items is that they generalize tables. Because if you think of that, how could you express a relational table as a sequence of items? Do you agree that a relational table would just be a huge collection of flat objects that all have the same keys and the same types? Who sees that? Some of you. Focus on that part of the screen. Let me ask you, pointing at this here, who agrees that this is a relational table? Right? 2 columns, foo and bar. Foo is an integer, bar is a Boolean. So relational tables are captured by sequences of items, but sequences of items are more generic because you can even have a huge mess and that will still be a sequence of items, or you can have also a sequence of Booleans, a sequence of integers, or a single value, or an empty sequence. And here are the relational tables. So you see, it's much more general than just relational tables. That's the power of a language that is built for trees. So you have the whole spectrum from highly structured to completely unstructured, that's all supported. And the reason, again, because somebody asked the correct question, like why do we need to support also data that isn't clean? Because in the real world, the data is often going to be like this. So you need a language that allows you to write in JSONic or whatever other language, you clean it up to turn it into something that looks like this, right? Because that belongs to the same language. Once you have cleaned it up, then you can start using machine learning on that. It's a whole ecosystem. Okay? All right. So that's it. That's my data model. It means that everything that JSONic manipulates is a sequence of items, right? It's also referred to as an instance of the data model, right? An instance of the data model is a sequence of items. Okay? Just like an object is an instance of a class in Java or Python. All right. So let's now start looking into the features of the language. It's like a Lego game, so I just need to give you all the Lego pieces. The first thing you can do is navigate. So imagine that I have, in that case, I'm taking a single document. We'll see it also can have billions of documents, but let's take that document. It has an array of objects inside that's nested. If I use JSON doc, not JSON file, JSON doc opens one document, gives me a sequence of one item. It gives a sequence of one object. Okay? So that returns this object right there. Now, if I add dot countries, it navigates inside that object. Dot countries is going to go down and take the value associated with countries, which is an array. And an array is the same as a sequence of one array, right? So this query here returns a sequence of one array. Who is with me? Okay. Now, what happens if I add this? This is called unboxing. I open the array, right? I open it up and I take what's inside. This returns a sequence of 5 items, in that case, 5 objects, right? And that's it. Who agrees? Okay, so that's this double square bracket opens the array into object. And then if I add dot name, it navigates further, but you see it does it on every object that now I'm going to return a sequence of 5 strings. Who understands this as well? Okay, so this is called navigation. The ancestor of doing things that way is called XPath. That's also a W3C standard. It's done with XML using slashes, but in JSON with dots, it works in exactly the same way. And the dots shouldn't be very surprising because you also see them in Python to access dictionaries, even though the square brackets can also be used. And the same in Java, in C++, in many languages, people are used to using dots to navigate objects. Okay, I could also do it with codes, then I also get a sequence of strings, but you see this is how it works. So you see how with very little code, I managed to do something like that. Now, what's this? This is a filter. It's a predicate. I'm just looking for all these objects, the ones that I took from the array. I'm looking for all the objects, the code of which is CH. So in order to do that, I need to build a predicate. It's some sort of formula that would be a lambda. If you think of a Spark filter transformation and you put a lambda in there with the predicate function, that's the same. And here, the variable, so each object is the $. The $$ is one object at a time, one of them. And every time I do dot code, so for that one, for example, over there, dot code will be CH, then I compare to CH, returns true, so I keep it. If I took the second object, friends, dot code is F equals CH, that's false, so I don't keep it. Think of a Spark filter. In fact, it is implemented with a Spark filter behind the scene. It's just hidden from the user. For whom does that make sense? So with this filter, I'm only going to return the first object because it's the only one that passes the filter. Okay? And you can combine these dots and square brackets and filters in any way you want, in any order. It just streams through your collection. And then you can even continue with dot name and so on, and then access. So this answers the query, what is the name of the country, the code of which is CH, right? And on the exam, you might have queries like this in English, and you'll have to write down the JSONic that takes care of it. Okay, now if it's a collection of documents instead of a single one, just use JSON files. JSON file is going to return a huge sequence of objects. And then when you have this sequence of objects, you add a filter on code equals CH, right? Dot name, and that, sorry. So imagine you have billions of them, right? That's my collection. It's the JSON lines that I told you about, the format with one object on every line. That could be on S3 or Azure or even on your laptop in your local file system. You open that file with this function, then you filter on the code, selects that object, and that dot name returns Switzerland. This query returns a sequence of one string item. Okay, that is Switzerland. Okay, now let's use that to do schema discovery. Schema discovery is, again, what I tried to explain you with the keys. You have some data, you download it from the internet, but nobody told you what there is inside, and you just have to figure it out because you want to clean it up and prepare it for machine learning. So this is a bit more like a geeky screen, right? What you would have if you do it on the shell. Of course, you also have the Jupyter notebooks that make it a bit nicer, but in that case, I just did it on the command line window. So JSON file, blah, 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 blah. Notice that it's not S3, it's HTTP. It actually works. You can use JSON file or JSON doc with HTTP, and it works just fine, right? It's just going to download it from the web. So in that case, we download that sample. I think it actually exists. If you actually type that in Jupyter Notebook, it will work. It just warns you that that would throw 36,000 objects at you. And of course, since it's so respectful of you, it's not going to throw them at you. It just warns you, right? And it's only going to show you 200 of them. You can modify that. But typically, if you have a warning like that, it probably means you don't want to print it on your screen. Rather, you want to write it back to HDFS, you know, or some data lake because it's too large to fit on your screen. Okay. So now you can use, that's a new syntax element. This square bracket one extracts an item in a sequence. We start counting at 1 in JSONic, right? So 1 means we take the first item in the sequence. So JSON file might return billions of items, and square bracket 1 extracts the first one. So this returns exactly one object, a sequence of one object. Who agrees? Right? Who sees that internally, that could be implemented as a Spark collect one action? Who sees that? Inside, you can do a collect one hidden from the user, and that is what you then get and display to the user. Okay, now you start seeing how it plays with Spark, that you can have Spark behind. Now, keys is the function you already know. So in that case, that's a data set, git archive, and it returns here 8 different keys. So now you can imagine some sort of a data frame with eight different columns, right? In fact, it's not a data frame because the types are a bit of a mess. There's no schema, but you kind of get that there are 8 different keys in there. Okay. Then you can also navigate like this. Imagine that now you see these 8 keys. You see one of them is type, repo, arg, actor, public type. So let's take type and navigate with dot type, right? Now I do JSON file dot type. That's going to return maybe billions of strings that all correspond to the types. And it might be that there's also arrays and objects in there. I don't know, right? Just so far they are strings. Since it's heterogeneous, it could also be other things than strings. Okay. Now, what if I would like to know all of the unique values that are in there? Because here that might be billions. Well, I just add a function called distinct values around the whole thing, because I have a sequence of strings. Distinct values is going to eliminate the duplicates. And now, this is it. That's just all there is as distinct values. Who sees that, again, you can actually do it in Spark with a distinct transformation? You remember? You can all do that in Spark. So it means that this also works if there are 1 trillion objects in the collection, will work just the same way, because in the background, you can actually use Spark. Then the same with created at. So here it's a count. Like imagine that you want to know how many distinct values are there for created at, and it tells you there are 3,597, right? What if you want to count the number of items in the collection? Just use counts around the JSON file, tells you there's 36. Now you can scale up. It works just fine, even if you have a bigger file. So here I downloaded a bigger one locally, so I don't have HTTP anymore because I'm reading it from my local drive. I have 200. What if I want to scale even more? Well, in fact, you can go there and download anything you want. It's all these zipped files that contain the data set. There is one every hour, technically a new file every hour. And then you can download them to your laptop. Now you will quickly notice it doesn't fit on your laptop, so it's actually a better idea to download them to S3 or to HDFS or whatever system you want. But basically, once you have downloaded a lot of this data, maybe a few terabytes or a few petabytes to HDFS, and assuming that HDFS is the default file system you read from, star.json.gz is going to take all of these files, and you see this query is just one line. It's just one line, but you might be reading from 1,000 different files, from petabytes of data. And here I actually did it. I executed that query. I put it on S3, I think, and executed that on the Amazon cluster. And it did answer me 2,013,245,097 objects. And that was relatively fast because, again, that's done with Spark in the background, right? You just have a creation that opens the collection. as an RDD, and then you call count as a Spark action inside, and it returns the total number. What's magic is that it's exactly the same query. You see, it doesn't matter where you read it from, it doesn't matter how large it is, it's always the same query. And you don't have to worry about how Spark would do it, because that's all hidden and implemented for you. Who is with me? All right. Let's continue. So let's do it with a filter now. You imagine you have an enormous petabyte data set, and you do $.type equals push event. So you're asking for the ones that match push event. You could also put an equal sign in there instead of AQ. There is a subtle difference, but it works too. And now it's going to output the subset of the events that are of this type, right? And you see on the first row of the object, type push event, right? So that fulfills the predicate. Okay. So that's how you can filter. Again, it would be a Spark filtering transformation behind the scene. Okay, so that's a bit of exploration. Try it, download the data set from the internet as JSON, Parquet, whatever, and you can go ahead and query it in that way to discover the schema. Now let's dive a bit more into the language. What about constructing new items? Well, that's actually an easy part, because it's a declarative language. So if you want to construct a new item, you just write it down. And in fact, every JSON value is also a JSONic query that returns itself. This is JSONic. You can type that in the Jupyter notebook, like string foo, and it returns itself. This is all JSONic. You can use the backslash escape, just like in JSON. That works in JSONic too. And these are all queries. These are 3 different queries that return one item, one string. Okay? This is the same with the numbers. So you can have 42, blah, blah, blah. These are 3 different queries, and they just return themselves. They return the numbers. Note that in JSON, there are only numbers, right? It's just number. But JSONic is a bit smarter because it has the whole type system that we saw, that we covered with JSON back then, JSON schema. It's the same as in XML schema. It's exactly the same list. So it's smart. If it sees there's no dot, it's going to make an integer. If it sees that there's no power of 10, it's going to turn it into a decimal with any precision, not infinite, but unbounded precision, and double for the scientific notation, right? It's this IEEE 754 standard for 64-bit double computations. Who is with me? Right? So these are all queries in JSONic. These are also queries. True, false, these are queries that return Boolean, right? True returns true and false returns false. Now, what about other types? That's called a cast. So if it's something else, you can create any other type, like long, in, short, byte, and so on, all the atomic types. Just put the literal inside a string, and then wrap up with a cast. You can create a non-negative integers. You can create a time if you use the time format, a date time, and so on. Any of these, even hex binary if you put the base 16, base 64 binary if you use the base 64 encoding, and so on. So that's how you create any type. So you see how JSONic doesn't limit itself to just number, string, Boolean, null. It can support any of the types that you find in XML schema, JSON, and so on. Okay? Good. Now, how do you construct an array? Well, you just write down the array. Here it's an array of objects. You agree with that? That's JSON, right? That's well-formed JSON. Well, it's also a JSONic query. You can put any well-formed JSON, put it in there. It's just a JSONic query. It's just returning itself, right? So that's, you will get exactly the same thing in the outputs. What about sequences? Well, if you want sequences of several items, just use a comma. So here we have a sequence of 4 items returned by this query, an array, and then a Boolean, and then a string, and then an object. I told you that it's heterogeneous, so you can actually mix that without any problem, right? The items do not need to be of the same type. You can also use 2 in order to build sequences. This builds a sequence of 100 integer items, right? Who is with me? Okay, so that returns 100 integer items. By the way, if you do 1 to 1 billion, you could also write 1 to 1 billion. You end up with a sequence of 1 billion items. But JSONic is going to be smart enough to actually do it in parallel. So if you're on an Amazon cluster and you type 1 to 1 billion, it's going to smartly create these billion integers in parallel on the machines. right? For example, it's going to put on the first machine 1 to 10 billion, and then on the second machine, 10 million and 1 to 2 to 20 million, and so on, right? So this is going to be very fast, even if you create a billion, a range of a billion, right? All in parallel. Okay, so that's to construct. So that you've seen, if you did the tutorial, you already know. What about arithmetic? Well, you have addition, you have subtraction, you have multiplication, you have division. Division is div, not a slash. This is because the slash is actually used for XML in XPath. That's the reason why the slash is not reused. So it's div, idiv is integer division. Who knows Euclidean division? It's basically the whole part of the quotient, right? And then you have the modulo, right? Okay, so this is arithmetics. Note that arithmetics works in the particular case that you're manipulating sequences of one item. So you have on the left one item, you have on the right one item. You add them, you get again a sequence of one item, right? It also works on the empty sequence. If you try to use the empty sequence, it's just going to return the empty sequence, right? However, if you try to use it on things that are not numbers, like strings and so on, then that's going to return an error. For advanced users, it actually works also on dates. If you put a date on the left and a duration, a number of days on the right, it is actually going to return the date, adding the days to the date. So it's actually smart enough to work also for date time, but just focus on numbers right now. So this is an error because you cannot add an integer to a string. And that is an error too, because here you're trying to work on sequences of more than one item. On the left, you have a sequence of 2 items, so you cannot add 2 to a sequence of 2 items. It needs to be at most 1 item on both sides. Who is with me? Okay, so that's arithmetics. Now, if you want to concatenate, you use the double vertical bar, or you use the concat function. String join is very useful if you have a very large sequence of strings, like 1,000 strings, and you want to concatenate them, but put a point or a dash in between the strings. Whoever tried to do it in Python or Java knows that it's not straightforward because you need to make sure that you don't add it in front of the first one or after the last one. So it's actually not so easy, but with a string join in a functional language, it's actually much easier. Substring takes a substring of a string, so a part of it. String length, that would return 6 in that case. That's the usual thing you have in many languages, right? So there's plenty of built-in functions that work on strings, very similar also to Excel formulas, if you think of that. So that's there's like maybe 200 standardized functions. It's all standardized by the W3C, most of them, so all nicely documented and available online. Then there's comparison. Comparison is just the typical signs: equal, different from, greater than, strictly greater than, lower equal, greater or equal, and so on, right? So it's just like in many other languages or even in Excel. Who is with me? Right? So that should be the easy part. Here it's an error because you cannot compare a string to an integer. Note that MongoDB would not throw an error on that, right? But MongoDB is very flexible. But in JSONic, you do throw an error if you try to compare things that are not comparable. Now, a nice feature of this comparison is that it also works on sequences. In fact, when you do it on a sequence, it tries to find a match on both sides. It's going to return true if it finds an item on the left and an item on the right that fulfill the criteria. Here is going to return true because you have the one that is equal to 1. In other words, whenever you use a comparison on a sequence of more than one item, it's going to apply an existential quantification, right? The exists in mathematics. It's going to return true if there exists an item on the left and there exists an item on the right that fulfill the comparison criteria. Who is with me? Okay, so in that case, for example, it's true because we have one that is lower than 3, and that's enough. You just need to find one pair like that, and that's enough to be true. Here it's false because you will never find anything on the left that is greater than or equal to anything on the right. So that returns false. Okay, and here it's an error because you're comparing a string to an integer, right? Here, that would be false, but this is simply because mathematically, if you try to use exists on an empty set, it's always going to return false. If you say, does there exist a member of the empty set that fulfills that and that? It's the empty set anyway. There's nothing in the empty set, right? So there never exists anything in the empty set. So this is why if you have the empty sequence, that's going to be false, okay? And how is it useful in practice? Well, imagine that you have a huge collection and you navigate it to the names. So on the left, you have the sequence of the names. Now you just write equals Switzerland, and that's going to return true if at least one of them is Switzerland. So it allows you to have a very compact query that checks if your collection contains Switzerland, right? So that's the idea. Okay, then you have logic, and or not, right? So that's just the usual, like in many other languages. It's just that in some languages like Java, and is a doppel ampersand, or is a double vertical bar in some languages. Here it's an explicit and, an explicit or, an explicit not, right? Who is with me? Right? So that you can combine in any way you want as well. Okay. I think you deserve a break, right? So let's take a break, 15 minutes. Then I'll talk about composability and I'll keep introducing other Lego components to the language. All right, so see you in 15 minutes. Thank you.